get rid of everything from here to here, right? And I'm going to comment it out and code something that is far superior. So I'm going to loop for k goes from 1 to n element. This is the loop over k, right? This most auto loop over k. And then I want to compute these element matrices. And I know every element matrix only have 4 non-zeros, right? So why don't I just set them as a small a11, a12, a21, and a22. How about that? Okay, I know my a11 corresponds to when I is equal to k, j is equal to k, right? My a12 is I is equal to k, j is equal to k plus 1. And a21 is equal to I when I is k plus 1, j is equal to k, and a22 is when I is equal to k plus 1 and j is equal to k plus 1. So just these 4 numbers to compute. And if you plug in the math, a11 is actually equal to 1 over xk plus 1 minus xk. All right? So that's what a11 is. It's just the integral of the square of the left derivative over the domain. And a22 is exactly the same because the derivative of the other basis function is the same in magnitude but opposite in sign. a12 is actually negative of this because I'm multiplying 2 basis functions. One have a positive and the other have a negative slope, right? But the magnitude is the same. And a21 is actually the same. All right. So it's interesting that they are extremely easy to compute and pretty natural. And the only thing left is to assign them to different places. So a of basically k to k plus 1 and k to k plus 1 is equal to the same thing plus a11, a12, a21, a22, right? So basically I'm incrementing the matrix, adding essentially the contribution of this element to the matrix. Okay, and if you run this and look at A, I'm basically getting the entire matrix, right? No matter which part you want to extract. If you fix the 2 boundaries, you only need the interior portion of the matrix. If you fix the right boundary and the left boundary has a Newman boundary condition, you not only know the derivative, don't know its value, then you want to keep everything except for the last row and last column. If on the other hand, you know the left value, but the right hand side, you only know the derivative, you keep everything except for the first column and the first row, right? So this is really the entire matrix you need. And similarly, you can assemble the right-hand side in an element by element way. So essentially, let me just write it down because we are running out of time. It's integration over also an element of phi times f dx. Okay, and that also makes the code a lot easier to write. So so instead of having b constructed like that, I'm also going to comment it out. And I also, well, sometimes you can write it in the same loop, right? So again, I have this loop over k, but I have just 2 non-zero entries, b1 and b2. My b1 in this case is equal to x k plus 1 minus xk divided by 2, and my b2 is actually the same thing, right? Because I have 2 triangles, one sloped in one way, one sloped in the other way. My b of k to k plus 1 is equal to b of k to k plus 1 plus b1, b2. Okay, so this is another natural way to construct my b. So this is the right-hand side, and essentially it's the same thing as before, but now since I'm constructing element by element, there is no special cases, right? No matter if it's on the boundary, not on the boundary, everything is the same. And this generalizes really naturally when we go to 2 dimensions and 3 dimensions. Okay, let's briefly talk about that in the next lecture before we move on, because the project I'm going to release over I think on Friday is actually going to be using a lot of what we talked about today. All right, any questions you have before we end this lecture? No? Okay. So yeah, feel free to ask questions on Piazza, and I'll post the project pretty soon. All right.
Thank you.
Yeah.
Thank you.
All right. So Michelle, I think let's go to a different Zoom meeting for the midterm. All right.
Yeah, sure.
Okay.
Just send me the info.
All right. I think Corey sent you the info.